Hi 7th grade Trailblazers, this is your video for the week of October 19th. So we're going to talk about reflection of mirrors. Last week we talked about the electromagnetic spectrum, which describes all the different types of waves that travel with electromagnetic radiation. Alright, so when we think of light waves, we're talking about visible light. We should think of them as straight lines called rays of light. So even though they're waves, think of them as straight lines. Surfaces can reflect this light in two ways. They can regularly reflect the light or they can diffusely. We're going to see that regular reflection shows the image perfectly while diffuse reflection does not. So the law of reflection, it's pretty easy. It sounds scary and ominous. Remember, laws are something that we see that happen consistently over time. So the law of reflection states that when a ray of light reflects off a surface, the angle of incidence, so that's this one right here, is equal to the angle of reflection. So think of them, if it hits at a 90-degree angle, it's going to reflect at a 90-degree angle. That's all. Pretty easy. That should make sense. All right, regular reflection occurs when parallel rays of light, see they're all parallel rays of light, hit a smooth surface. The surface is smooth, like this body of water. All the rays reflect at the same angle because of the smooth surface. You see a clear image. Now, image in this case means a copy of the object formed by reflected or refracted rays of light. So if we see the images in the water, we see that it's a perfect copy. It's a nice image. Diffuse reflection is different. Diffuse reflection occurs when the parallel rays of light hit an uneven surface. So this body of water is uneven. So each light ray still obeys the law of reflection. It hits the surface and it reflects at the same angle of incidence. But because the rays hit at different angles, the image that we see is not clear. Okay, sometimes we don't even see an image or it's blurry. That's why this otter looks really blurry. His reflection is diffuse. All right, so here's just another image. Regular reflection happens when it hits a smooth surface. We get the same image. Diffuse reaction, we can see they all hit, but because the surface they're hitting is uneven, the light rays are going to bounce off and make the image look blurry. Alright, so let's talk about some things that these images can bounce off, like plane mirrors. So plane mirrors are probably what you have in your bedroom or in your bathroom. They're a flat sheet of glass that has a smooth silver coating on one side. So when light hits or strikes a mirror, the coating reflects the light to produce a virtual image. So a virtual image doesn't really exist. Like, there's not another person here, but it just shows where the light seems to come from. So a plane mirror, and there's going to be different types of mirrors, a plane mirror produces a virtual image that is upright, so it's the same, going in the same direction as the thing making the image, and it's the same size as the object. So we want, plane mirrors are what we look in to check our image or whatnot. Alright, so let's go back to what different types of mirror. A mirror that with a surface that curves inward like the inside of the bowl is a concave mirror. Okay, so you see how it's shaped like a bowl. They reflect parallel rays of light, so they meet at a point. So it doesn't matter where they're coming from. Because this angle is curved, they're going to come back to this specific point. The rays of light are parallel to the optical axis. That's this thing in the middle here, this optical axis. It's an imaginary line that just divides a mirror in half. The point at which rays parallel to the optical axis reflect in me is called the focal point. And we see that right here in green. Concave mirrors can produce real or virtual image. Okay, a real image forms when light rays actually meet. And we know what a virtual image is not really there. Objects farther away from the mirror okay, so you have two different things. Objects farther away from the mirror than the focal point form a real image. Real images are upside down though, so that's what's different with concave mirrors than plane mirrors. They're upside down. Remember, plane mirrors were upright. The opposite of concave is convex. So we see instead of coming in like a bowl, it kind of curves outward like a contact lens or an eyeball. What happens here is when we get the reflected rays, they spread out, but they still appear to come from behind the mirror at the focal point. So the focal point here seems to be behind the mirror. The focal point of a convex mirror is the point from which the rays seem to come from. A convex mirror does the same thing. It doesn't produce a real image, it produces a virtual image, and this one is the one that's smaller than the object. Alright, so the next time you're driving in a car, it might be not the rear view mirror on your passenger side, but if you can look in the one on where your parents are driving, they probably have like a little teeny mirror in the corner, and then they have a regular mirror. The one in the corner is actually a convex mirror, and it might say on it, objects from this mirror are closer than they appear. So they seem to be, things are smaller, they seem to be farther away, but they're really not. Alright, so light. When we talk about visible light spectrum, when it hits an object, it can be reflected, means it bounces off. It can be refracted, meaning it's bent, or it can be absorbed into whatever it's hitting. So let's talk about refraction first, because we just talked about reflection with mirrors. Refraction is the bending of light, and it occurs to light rays when they hit different mediums. When I mean mediums, I mean solid, liquid, gas. So light bends when it passes from air into water, or etc. So if you look at the straws, these straws, they're not really bending. What's bending is the light. So because the light is in gas and then it hits the water, the light appears to bend. It is bending, but it makes the straw appear to bend. So the index of refraction of a medium, so the medium in this case can be any of these things. And a vacuum means that there's no material. Air, ice, water, vegetable oil. It just shows how much light rays bend when they hit that medium. So air, they bend a little bit, but when we look down here, something like glass is going to cause light rays to bend a lot. Alright, prisms and rainbows, pretty stuff. When white light enters a prism, and you probably played with a couple of these in class, or you will when we do a lab, each wavelength is refracted by a different amount. So this has to do, when we talked about the electromagnetic spectrum, every color of the visible light has different wavelengths. Okay, so the longer the wavelength, the less the wave is bent. So, for instance, red has the longest wavelength, is refracted the least, means it doesn't bend that much. Violet, at the end of the visible light spectrum, has the shortest wavelength, which means it's bent the most. The difference in refraction causes white light to spread out into the colors of the spectrum when it hits a prism. Okay? Alright, mirage. Mirages are cool. Maybe you've seen them when you're driving down the highway and it's really hot in the summer. But it's an image of a distant object caused by that bending of light. So normally we know that light waves from the sun travel straight through the atmosphere to your eyeball. But light travels at different speeds through hot and cold air, and we just talked about why. We just talked about that visible light spectrum has different wavelengths, and when it hits different mediums or prisms or whatnot, it's going to bend a little bit differently. So light travels at different speeds through hot and cold air. Mirages happen when the ground is very hot. So ground is hot, this is why I said the summer, and the air around it might be a little cooler. So mirages tend to happen in early morning maybe, or mostly though late afternoon when the ground has been heated all day and then it starts to cool down. So the hot ground warms a layer of air just above the ground, so it shows it in this orange stripe in the image. So when the light moves through the cold air, cool, and then it hits the hot air, it's bending. So do you see this bending? So it's refracted. So a layer of very warm air near the ground refracts the light from the sky nearly into a U-shaped bend. So you see this nice U-shaped bend. Our brain thinks the light has traveled in a straight line. Our brain doesn't see the image as bent light from the sky because we can't see that actual bent. Instead, our brain thinks the light must have come from something on the ground, maybe a puddle of water, or maybe if we're driving down the highway, we think it's a puddle of gas. So mirages tend to happen. We hear them speak about, desert cultures. They're hot, they're tired, they're traveling, maybe with all these camels. And up in the distance, finally, they see, oh, it's a watering hole. And they keep traveling, and then they get there and there's no water hole. It's because they saw a mirage. All right, speed of waves. So the speed of waves through a substance is determined by the substance's physical properties. So here's what's important. Speeds of waves in a vacuum, that means in space, if there was no material, they travel at a consistent speed. Okay, so that is the speed of light. all electromagnetic waves travel at 300,000 kilometers per second in space. Okay, that's a vacuum. However, when they enter an atmosphere like Earth's and they have to go through different material, it's going to either, it's never going to speed up, it's just going to slow down. It can't go faster than 300,000 kilometers per second, but they certainly go slower. And we see that when we travel through air or atmosphere, it's less than 300,000. Water is even less, 226,000. Glass, diamond, so forth. If we kept going down to like oil and stuff like that, it would slow down. So sound waves do the same thing. They also travel at different speeds through different materials, and we'll play with this in class a little bit with some tuning forks. So temperature, density, and compressibility can also affect the speed of sound waves. So what I mean by that is temperature. If we increase the temperature of an object, or decrease, we can speed up or slow down the speed of sound. Density, if it's a very thick, viscous liquid, the speed waves are going to go much, much slower. Or sound waves are going to go much, much slower. And if we compress or put more air or more material in a specific thing, that can also slow down the speed of sound waves. And that's it for this week, and you guys have a great day.